Number 3, Chapter 6, Section 1, Angles and their Measures. First of all, we're going to talk a little bit about trigonometry, and trigonometry means measurement of triangles in Greek. It was used in the development of astronomy, navigation, and surveying, and they were used to find angle and side measures. With the development of calculus and the physical sciences, trig relationships became viewed as functions with a set of real numbers as their domains, instead of just being measurements. This allowed for a wider range of application that included rotations and vibrations. And some of the phenomena that trigonometry functions explain would be sound waves, light waves, planetary orbits, vibrating strings, pendulums, orbits of atomic particles, just a lot of applications for trigonometry. First of all, an angle in trig is determined by rotating a ray around its endpoint. A way to think about it is think of the hands on a clock. Think about both of them pointing at 3, and then the big hand moving either clockwise or counterclockwise from there. The small hand would be the initial side, and where the big hand ends up is the terminal side. The pivot point of the hand, where they're connected in the center, is called the vertex. When the vertex is at 0, 0 on a graph, on an XY graph, and the initial side is the x-axis, we say the angle is in standard position. Now, in geometry, angles were always positive. Now they can be positive or negative. Positive angles rotate counterclockwise from the initial side, as you see here, and negative angles rotate clockwise from the initial side, as you see here. Notice the little curve with the arrow on it indicating which direction the angle has rotated. It is important that when you draw these angles, you include that curve. Angles can also now be greater than 360 degrees. Angles can be formed by circling the terminal side all the way around one or more times before finding its final position. Because of this, one arrangement of the two rays, the initial side and the terminal side, can represent many angles, both positive and negative. So if you look at this diagram, you see the initial side and the terminal side. The smallest positive angle there is 55 degrees, but if we start at 0 and we go all the way around and back to that angle, that's 415 degrees. Or we could start at the initial side and go clockwise, which would make it a negative angle, and that would be negative 305 degrees. So many different angles are represented by the same setup of initial and terminal sides. And those angles that all are represented by the same setup are called coterminal. Angle measure is determined by the amount of rotation from the initial side to the terminal side. Degree is the most common and is what you're used to using. 1 degree is 1/360th of a rotation because a circle has 360 degrees. This is the Greek letter theta, and it is a symbol that you use commonly in trigonometry to symbolize an angle measure. A few things to remember: an acute angle will be between 0 and 90. A right angle is exactly 90. An obtuse angle is between 90 and 180, and a straight angle is exactly 180. A full rotation around the circle is 360 degrees. Okay, this is a setup of the degrees laid out on the XY graph. Notice that the X and Y axes separate the graph into 4 quadrants. You've talked about those before in math class. The upper right is 1, the upper left is 2, the lower left is 3, and the lower right is quadrant 4. And you can see the different angles there. All of the ones, you've got 30, 45, 60, those are our special angles. Those were the special angles you learned about in geometry and from the special triangles. The rest of the angles are really multiples of those. 60 times 2 is 120, 60 times 3 is 180, 30 times 4 is 120, 30 times 5 is 150, and so forth. First task is to determine which quadrant each angle lies. Pause the recording, try these out, and resume to check your answer. Also, go ahead and sketch the angles in standard position. Okay, the first one is quadrant 3. 132 degrees, 50 minutes. Don't worry about the minutes part. If you got the 132 degrees and focused on that, you'd be fine. And negative 336 would be in quadrant 1 because you're going backwards around the circle. Okay, 30 degrees looks like this in standard position, and 150 would look like that. Okay, two angles are coterminal, like we've said before, when they have the same initial and terminal sides. And here's a couple of examples. Okay. You can find coterminal angles very easily by adding 360 or subtracting 360 from an. So find two coterminal angles for each angle. Just take the number, add 360, and then take the number and subtract. Pause the recording, give it a try, and resume to check your answer. See how you did. Notice that with the subtraction, it's really important that the 360 comes second. Also notice with the negative 520, you can, and these are not the only possible solutions. You can add and subtract 360 multiple times to get more angles. Notice they did negative 520 plus 720. In other words, what they did is they added 360 twice. That's where that came from. And they didn't subtract because you can actually add and still get a negative with that. You may have gotten different answers, but did it right. So there's, like I said, there's an infinite number of possible answers here. Degrees can be broken down into minutes and seconds. 60 seconds is 1 minute, and 60 minutes is 1 degree. To convert degree, minutes, seconds to decimals, you're going to do the degree plus minutes over 60 plus seconds over 3,600. And to convert degrees to minutes, the decimal to degrees, minutes, seconds, subtract the whole number, multiply the decimal by 60, subtract the new whole number, multiply that decimal by 60, and what you have left is the seconds. The whole number of that would be the seconds. Your calculator will do this for you. To convert a decimal degree to degree, minutes, seconds, enter the decimal, then push second apps, and choose degree, minutes, seconds, DMS. Hit enter and you've got it. To convert degrees, minutes, seconds to decimals, put in the degrees and then press second apps and choose the degree symbol. Put in the minutes and then press second apps and choose the minute symbol. And then put in the seconds and choose alpha plus. That's where the seconds is. And then hit enter and that'll convert. So try that now with these two. I would use the calculator and not the manual way of doing it. So pause the recording, give this a try, and resume to check your answer. Now here we do have it worked all the way out for you. Again, it's fine to use your calculator for this. Complementary and supplementary, you should know already. Complementary are two angles that total 90. Complementary angles total 90 degrees. Here are some examples. They do not have to be connected, but they may. And supplementary angles are two angles whose measures total 180. Again, it's not necessary that they're connected, although they could be. Now find the complement and supplement of each angle. Pause the recording, give it a try, and resume to check your answer. Notice 126 degrees has no complement because they have to total 90. Now we're going to get into radian measure. A radian is defined using a central angle of a circle that is centered at 0, 0. 1 radian is the measure of a central angle theta that intercepts an arc S equal in length to the radius r of the circle. Algebraically, the angle theta is S over r. So when the arc length and the radius are the same, you have an angle that's 1 radian. The circumference of a circle is 2 pi r. So the central angle of one full trip around the circle has a matching arc length of 2 pi r. So your circumference is 2 pi r, your arc length is 2 pi r, and then using our formula, if S is 2 pi r over r gives us 2 pi. What that means is a full circle in radians is 2 pi. In degrees it's 360, in radians it's 2 pi, which means that 90 degrees is pi over 2, 180 is pi, 270 is 3 pi over 2, and 360 is 2 pi. Here is the same chart I had earlier. It's slightly different, but it's the same idea with all the special angles on it and their radian equivalents. And you're going to get very familiar with these. All right, now try to figure out which quadrant these angles lie in. And these are all in radians. Pause the recording, try it out, and resume to check your answer. To find an angle's complement in radians, we subtract it from pi over 2, which is the equivalent of 90 degrees. To find its supplement, we subtract it from pi. Coterminal angles, remember for degrees we add or subtract 360. For radians, we add and subtract 2 pi. Honestly, the sooner you get these equivalences in your head, it's going to make it a lot easier. 360 is 2 pi, 180 is pi, 90 pi over 2. Try these out, pause the recording, and resume to check your answer. Okay, converting. Remember, there's 360 degrees in a circle. There are also 2 pi radians. So what I like to do is use a proportion. 360 over 2 pi is 180 over pi. 180 degrees over pi. We'll just set that up. What you're going to do is you're going to do 180 over pi equals, if they give you the degree, put the degree on top, x for the radians, and solve. For when they give you radians, you just put the radians on the bottom, put x on the top for degree, and solve. You're just going to cross multiply. Pause the recording, give these a try, and resume to check your answer. Okay, try these out. Pause the recording, give them a try. On these, you're going to actually put it in your calculator and get a decimal answer. Resume to check your answer. Okay, a few applications. Arc length for a circle of radius r. A central angle theta intercepts an arc of length s, where s equals r theta. In other words, the arc length is r radius times theta. However, the angle must be expressed in radians. So in other words, the length of an arc equals the radius multiplied by the measure of the radians of the angle that connects with that arc. Now try these out. Pause the recording, give them a try, and resume to check your answer. We also have the area of a sector. The area of a sector formula is a little bit different. Sector is a pi piece. Area equals 1/2 r squared theta, where theta is measured in radians. So you're going to multiply 1/2 times r times r times. Try this out. Pause the recording. Try it out and resume to check your answer. Okay, let's talk about some applications, or some more applications of angles and radians and all that good stuff. First of all, linear and angular speed. Consider a particle moving at a constant speed along a circular arc of radius r. Maybe picture a circular toy car track with a car going around it, a remote control car, and you got it going at a constant speed. If s is the length of the arc that the car has traveled in time t, then the linear speed, or v for velocity, of that car, of that particle, is v equals s over t, or linear speed, velocity, equals the arc length over time. In other words, how far it went divided by how long it took to get there, which makes sense. We've done that before. It's just instead of actually being in a straight line, it's curved. Now we have a different type of speed that's associated with motion in a circle. We also have what's called angular speed. Angular speed measures how fast the angle is changing from the starting point on. So it's how fast is the angle changing for the circular path of that car. So if theta is the angle that intercepts the arc of length s, the angular speed omega is omega equals theta over t. Angular speed is the angle in radians divided by time. So how fast the angle is changing is how much of an angle have we covered divided by how much time it's taken to do that. So what's the difference between linear and angular speed? Linear speed is how much distance the car, the particle, the whatever covers as it goes around. Angular speed is how fast the central angle is changing as that particle travels. Think about it, if you think about the hands on a clock, it's how fast is the angle between those two hands changing. I found this little cartoon a long time ago. It's old Calvin and Hobbes. The father says, "Are you playing a record? I'll show you something interesting. Compare a point on the label with a point on the record's outer edge. They both make a complete circle in the same amount of time, right? But the point on the record's edge has to make a bigger circle in the same time, so it goes faster. So the 2 points on the disc move at 2 speeds, even though they both make the same revolutions per minute." And again, and then poor Calvin looks traumatized by this whole thing. But it's just kind of illustrating the difference between angular speed and linear speed. Or think in terms of a merry-go-round. Think about the horses that are closer to the center, or a carousel. Think about the horses that are closer to the center versus the horses that are closer to the outside. If you want a faster ride, you're going to ride the outside horses. Because even though 2 horses that are in the line are going to be traveling at the same angular speed, the angle is going to be changing at the speed for both. The one on the outer edge is actually going to be going at a faster velocity because it has to go all the way around the circle in the same time that the inner horse goes all the way around the circle. A little bit weird, but it just kind of shows you the relationship. All right, let's try a word problem with this. We have a satellite in orbit. It's 1,250 kilometers above the Earth, and it makes one complete revolution every 110 minutes. Assuming that the Earth is a sphere of radius 6,378 kilometers, what is the linear speed of the satellite? Velocity equals the arc length over time, and if you remember, arc length is radius times the angle. So what we need to do is we need to kind of put that information together. I'll give you a hint. The radius for the satellite is going to be the radius of the Earth plus the distance above the Earth it is. Why don't you pause the recording and give this a try, see if you can sort it out, and then resume and we'll look at how you did. Okay, so our linear speed is s over t, and s is r theta over t. And so like I said, the radius, we need to add the Earth's radius. We need to add that to the distance that the satellite's above the Earth. And it's making one complete revolution. Well, that means it's completing a circle. So it's gone through an arc of 2 pi, and it does that every 110 minutes. That's the hard part. If you get all that sorted, then what you need to do is go ahead and just do the math, and you get that it's about 435.7 kilometers per minute. All right, let's try a couple of other examples. Why don't you look these over and pause the recording, and then resume and see how you did. Okay, so we have a DVD that's approximately 12 centimeters in diameter. Now remember, we need the radius, so you're going to have to cut that in half. The drive motor of a DVD player is controlled to rotate precisely between 200 and 500 revolutions per minute, depending on what track is being read. Find an interval for the angular speed as it rotates. In other words, you have 200 to 500 revolutions. So what does that mean as far as angular speed? It's between what 2 numbers? All right, so there we go. We know that it goes between 200 and 500. Now, a revolution is 2 pi. So 200 times 2 pi and 500 times 2 pi. So that means, and it does that every minute. So it's going between 400 pi and 1,000 pi radians per minute. And then we're supposed to find the interval for the linear speed of a point on the outmost track. Now remember what we said, the linear speed is going to be highest on the edge of the circle. So the linear speed, let's see, the radius is 6, so it's going to be 6 times 400 pi and 6 times 1000 pi. So the interval is between 2400 pi and 6000 pi centimeters per minute. Okay, here's another one. A car windshield wiper rotates 125 degrees. So be careful where this is in degrees. Remember, our formulas require radians. The total length of the wiper mechanism is 25 inches, and the length of the wiper blade is 14 inches. Find the area wiped by the wiper blade. I suggest you make a little bit of a sketch of this first. Why don't you pause it, give it a try, and resume to check your answer. Okay, so there's our sketch. We see the 125 degree rotation. We have a radius that's not covered. Okay, the total length is 25, the blade's only 14. So you can subtract and discover that we've got about 11 inches there that are not covered. Okay, so our area. Now, there's two ways you can do this. They kind of combine the formula here. Remember, our area formula is 1/2 theta r squared, or 1/2 r squared theta. What you want to do is you want to find the area for the outer circle, the whole thing, where your radius is 25 inches. You want to find the area for the inner one that's not getting any clearing at all, the one that's 11 inches. And then you want to subtract the two areas. Well, what they've done here is they've actually kind of combined those two formulas into one. So you can actually do it the way they're doing it here, or like I said, you can find the area of the outer circle, or the outer arc, the area of the inner sector, and then just subtract them. And either way, you're going to get 549.8 inches squared.